In the previous video, you saw a method for estimating the total amount of dust that would accumulate on the Mars rover's solar cells. The method that we used is in general called a Riemann sum. And in this video, I'll show you exactly what that is. So let's start by looking at another example. A scenario that you might be familiar with is accumulating distance when you're traveling. For example, let's say the function r of t tells you the number of meters a moving car accumulates per second. That is, r of t is really your speed. And let's say you collect some data that shows the rate of accumulation. So if you looked at the first interval from 0 to 2 seconds, that has a change in time of 2 seconds. For the rate for that interval, you could either use the rate at the beginning of the interval or at the end. For now, we'll use the value at the beginning of the interval. So you'd assume that you're accumulating distance at a constant rate of 1 meter per second, and you'd multiply delta t by the rate of accumulation for that interval, which would give you a distance of 2 meters. You could keep on doing this for each of the other intervals. And then you'd add them up to find that you've accumulated a total of 44 meters. We also could have done these computations using the endpoints of each interval, that is, the speeds at the end of each interval instead of at the beginning. So if we did this, you'd do the same thing as before. But, for example, in that first 2-second interval, instead of assuming that we were traveling 1 meter per second for the entire interval, you would assume that the rate was 3 meters per second for the entire interval. So you'd get a distance of 6 meters for that interval. If you do this for all the other intervals and added them up, you would get a total distance of 54 meters that we traveled. There are a couple of things to keep in mind here. First, we assumed that r of t was constant over each interval. So both the 44 meters and 54 meters are approximations of the actual distance we traveled. Second, you might be inclined to think that the 44 meters is an underestimate of the actual distance, and that the 54 meters is an overestimate. You might be thinking this for several reasons. One potential reason is because the 44 meters came from using the rates at the start of each interval. Another potential reason is that the 44 meters is less than 54 meters. Both of these might have you thinking that the 44 meters is an underestimate. However, this is not necessarily true. For example, if you look at the estimate for the second interval, we assumed that we were accumulating distance at a rate of 3 meters per second for the entire interval. However, we might have only been accumulating at a rate of 2 meters per second for most of the interval. So the 6 meters is probably an overestimate of the distance that we traveled for that interval. And since we used the 6 meters to compute the 44 meters, this means that 44 meters might not be an underestimate, and similarly, 54 might not be an overestimate. Let's look at how this all translates to more general mathematical notation. We had information about r of t, the number of meters we accumulated each second. Another way to think of this is as speed. Our goal was to find the total distance that we traveled. To do this, we looked at values for r of t. We assumed that r was constant over each time interval. And then we multiplied the value of r by the change in time to get the distance traveled over the interval. And then we added up all of these distances, starting at 0 seconds up to 12 seconds, to get an estimate for the total distance that we traveled. We got 44 meters when we used the speed at the beginning of each time interval. So this was specifically for speed and distance, but generally, you can use Riemann sums whenever you're trying to find the total amount of something that will accumulate. In the previous examples, we were accumulating dust and distance. To find the total amount of dust or distance that you would accumulate, you start with a rate of accumulation. So here, r of x tells you how quickly something is accumulating for each value of x. And then you assume that this rate of accumulation is constant over each interval that you're looking at. And then you multiply the rate by the size of the interval, delta x. And finally, you add up all of these products, which we write using the symbol called sigma. In general, this sum of products is called a Riemann sum.